In this lecture, we're going to be looking at an introduction to problem solving. Problem solving can be divided into a four-step process: understanding the problem, coming up with a plan, carrying out the plan, and then looking back to make sure you have a solid plan that did actually work. Now, the trick here is when we're problem solving, understanding the problem and devising a plan aren't going to look the same in every problem. It's going to morph, but we're going to want to follow these four steps in order as we begin to try to understand how we're going to solve each question. So, to understand the problem, think about it in your own words. How would you ask someone else this question if you were asking it yourself? Identify, what are we trying to find out? What are we trying to solve for? What are we trying to actually do? Then you want to figure out, what don't I know? So look for gaps in the problem, or even the last sentence might say, find the length. That's what you're looking for. Then you're going to determine any other information given in the problem that might be relevant. Maybe there's a shape, maybe there's a formula, those types of things. And then you're going to determine information that might be missing or not needed. A lot of times when we're problem solving, there's pieces of the information we may not need that may not be relevant to what we're looking for. So that's what that question really means. When we devise a plan, we're looking for patterns. We're looking for, is there a similar problem I may have done? Is there a simple or special case of this problem? And then we can start organizing the information. So making a table or a list is a really good way to do things. Maybe you're listing everything you know, and you're also listing what you don't know. Then you're going to get a sub goal. This is what I want to do. When I'm done with this problem, this is what I want to have done. And you make a diagram, a rough sketch. Drawing a diagram is so helpful, even if you're not artistically inclined. Then you can start applying some guess and check with what to do and work backwards to write an equation. So the end goal in these problem solving problems is we want to get to an equation so that we can carry out the plan. To carry it out, we're going to use the strategies that we thought of and when we were devising a plan. We are going to look at precision in language and mathematics used. So we're going to look for keywords in that language. We're not going to round until our final answers are done. And then we're going to check each step to make sure that we're not making algebraic mistakes. And we're going to keep an accurate record of what we've done so that we can double check our work. When you look back, you want to think about, does my answer make sense? If your answer is 5,000 feet, but the dimensions in the problem are like 2 inches and 5 inches, then that's really wrong. So you really want to stop and take that answer and put it in context and see if it makes sense. You want to interpret those results in terms of the original problem. Does it make sense? Is it reasonable? And is there another method I could have used to find the solution that might give me a different answer? If possible, you can look at other general problems for which these strategies will work. Now, I want to be careful with looking back. Typically, our gut instinct for how to do a problem is correct. So looking back is not second guessing yourself. It's just taking a quick look back to make sure that your answer makes sense. So in section 1, we want to be able to explain the four-step problem solving process that I just went over. We want to be able to solve problems using those strategies. So if we start taking a look at strategies, where does that put us? Well, strategies are different tools that could be used to discover what we're trying to do as our end goal. Because problems are solved in more than one way, there's no best strategy. How you solve the problem may not be how somebody else solves the problem, and that's okay. But that's also what's really challenging to teach our students about, is that they can go about things differently, but still get the right answer and still have correct math. So it's really important when you're teaching problem solving to make sure that they understand, as long as it's mathematically sound, there's no one goal strategy, as long as they're doing sound math. And then sometimes strategies can be combined in order to solve a problem. Maybe I have a two-step problem where I have to complete two different processes. So looking at patterns, Carl Gauss was a child. His teacher worked with students to find the sum of the first 100 natural numbers. The teacher thought this was going to take a really long time for students. However, Gauss got the problem almost immediately. And how did he do that? Looking at the natural numbers, those are counting numbers. So 1, 2, 3, 4. And the question she was asking was to sum the first 100 terms, which May sound a little bit easier than it actually is when you look at the actual series down there. You want to list the numbers as shown, is how we begin to work it. And then we start combining them, and look what happens. The sum of every column is 101. So then if I take the 2s and I divide it by 2, I get 100 sums of 101, which would be 5,050. So this was the process that Gauss used to solve what was going to be an intricate arithmetic process. Now, granted, you and I may not ever come up with that. We might have sat there and crunched those numbers. Again, it's mathematically sound. Not everyone's brain is going to be hardwired to find patterns like Gauss's brain was hardwired. Looking back, we know that it's correct because addition can be done in any order, and multiplication, like 2s, is really just repeated addition. So it was a mathematically sound method. It's not how everybody else would have gone about it, but it did result in an accurate answer much quicker. Now, let's look at finding the sum of the even natural numbers less than or equal to 100, and let's see how we can walk through that process. So I want to understand the problem. Here are my even numbers up to 100. I want to devise a plan. I'm going to start looking for patterns. Again, this is revealing Gauss's problem-solving process, which is quicker than other students' processes. He figured out, well, if I factor a 2 out, then I'm just summing the natural numbers to 50. He applied the same thinking he did to 100 and was able to get the answer much quicker. He then looked back. You double check things, make sure it's reasonable, make sure it's sound, and then you're done. One strategy for solving a complex problem could be to look at an easier case. And so it might be easier for the average person to look at just the first 5 numbers, and then maybe they could abstract the pattern for 100. So this is just talking about scaffolding. As we teach our students, we want to scaffold them from the simpler problems to the advanced. We don't want to just jump to advanced without giving them the proper tools to recognize the simpler part of the problem. This is often used strategy in elementary school called making a table. A table can be used to find those patterns that emerge in a problem that might could lead to a solution. So if I want to identify a subgoal within this realm, I could arrange the numbers 1 to 9 in a square that's divided into 9 subsquares. Then I would need to put the numbers into the squares. If we knew the fixed sum of the numbers in each row, column, and diagonal, we could have a better idea of how the numbers appear in a single row, column, or diagonal. That's a subgoal. It's a goal before I get to my final answer. So if I start looking at just that smaller problem, then I notice that it equals 3 times the sum of one row. So my fixed sum would be 15 if I took that and divided that by 3. Now, if I wanted to decide what would happen if I kept going, then I would look at 4 sums, each adding to 15 with the diagonals. So this is basically just scaffolding up on the plan. The takeaway here is we want to give students the tools to solve an easier problem before we begin presenting the tougher problem. So then we can look back on our answer and see if it makes sense. Now let's look at one where we have to make a diagram. And students, for some reason, don't want to make diagrams a lot of the times, and not everyone is artistically gifted. Me personally, I have wonderful stick people who do the job for me, and that's okay. So if we're looking at this word problem and we want to stop and make a diagram, so we could sketch something like he ran a 50-meter race 3 times. So I could have 3 lines. The speed didn't vary. And the first race, he was at the 45-meter mark when Bill crossed the finish line at the 50-meter mark. So that could be marked off as a little area there. In the second race, Jim started 5 meters ahead of Bill, who lined up at the starting line, who won the race. And then we have the third one. So we can kind of draw a little diagram to help us understand those distances and where somebody has started from to where they end to really get an accurate look at what the 50-meter race looks like. If I want to understand the problem, then I'm going to be using that diagram to start pick out intentional information. So when they both run a 50-meter race, Bill wins by 5 meters because whatever Bill covers 50, Jim is only covering to 45. If Bill starts at the starting line and Jim gets a 5 meter head start, how would we determine that? If Jim starts at the starting line and Bill starts 5 meters behind, how are we going to determine who won that? So this is kind of a look at the diagram that I would draw. I try to draw really basic diagrams. I'm not trying to be artistic with these. And I'm looking at the start and the finish here. And then I'm looking at race 2. This time we're having them start from the starting line and they're finishing. And then we have this situation where we're looking at giving them a 5 meter, Jim a 5 meter head start. From the diagrams, we can see the results of each case. And that's not really something that I had to do math for. Once I had a diagram, I really could look at things and I could figure out who won the race. Looking back, the solution should make sense and it's appropriate. Now, if I want to talk about guess and check, guess and check is something that a lot of people don't address because it can be a little bit like flying blind. But it's important for our students to try new things. We want to teach them to branch out and to try different things with their problem solving skills so that they can also grow. In some problems, it's going to be easier to start with the answer and then work backwards to figure out, well, how did I get that answer? So if I look at it, it took workers 5 weeks to dig a 10-mile tunnel. During the 4th week, they dug 2.5 miles. The next week, they dug 1.25, and so on and so forth. How much of the work is completed after the first 3 weeks of digging? It might be easier to take the ending point of 10 miles and then work backwards from that. So I would need to find how many miles of tunnel they dug in the first 3 weeks. Well, what if I look at it as taking away what they did the last 2 weeks so that I'm working backwards? Because that's the information that I'm given. So when I do 10 minus their progress, my answer is 6.25 miles. Now, does that make sense? Well, we're doing 10 miles total. If I take 6.25 and I add what they dug the last 2 weeks, it does in fact give me 10 miles. So if I wanted to check and see if it's reasonable, I would say, yes, that's reasonable. Now, writing an equation is just substituting an algebraic thinking. So with younger students, we don't typically tend to use variables. We like to use an empty box. This just helps them conceptualize, so they have to solve for what goes there. So this could be something as easy as 14 minus blank is 3, or 14 minus what is 3. We're really teaching them 14 minus x is 3, what is x? But we're taking out that middle step. It's going to be something that's a little more abstract that we want to present at those lower grades.